Hello everyone, today I'll conduct a topic review regarding deep neural network compression. First of all, I would like to talk about the motivation of deep neural network compressions. We are all aware that deep neural network has become the major driving force of advancement in various fields, ranging from computer vision, natural language processing, speech recognition, and other things. These advancements often come together with increasing model complexity, number of parameters, as you can see in the figures above, and then prediction latencies, and other intrinsic properties within the network itself that isn't mentioned here. As a study case, we first consider Megatron Turing NLG, a new language model released by NVIDIA and Microsoft recently that comes with 530 billion parameters, which is 3 times larger than that of GPT-3 released last year. While these models exhibit an advancement of Sultan in different tasks such as natural language, they might not be useful for practical applications, which is often bottlenecked by cost, mobility or inability for real-time or on-device deployment, and other things. So naturally, our question will be, how can we employ these deep neural networks efficiently? Meaning that how can we achieve maximum performance with minimum effort or expense using these networks? To achieve such goals, we often come up with 4 common approaches, spanning from compression techniques, learning techniques, efficient architectures, and automation, with each technique optimized combinations of performance and resource usage while leveraging the others. These techniques that is listed here is the most common technique used to achieve the goal of efficient deep learning. However, in this talk, I would like to focus more on the compression techniques employed for deep learning, notably pruning and rewiring. So what is neural network pruning? Pruning is a technique to compress neural network by sparsifying or zeroing out weights in a network that are not important. The motivation behind pruning comes from Optimal Brain Damage paper in 1989, which means that it is not an entirely new technique. The paper state that it is possible to take a network, delete some portion of its weights, and come up with a subnetwork that performs as well or better than the original network. Pruning is often the most popular way of compressing neural network due to its simplicity in implementation and tons of design choice that comes with them. This is the overall algorithm of neural network pruning. Taking W prime as the prune network parameters from a pre-trained dense network with parameters W, we first compute a saliency score S, which as a function of W prime, we apply such scoring method to W prime to cancel or zero out the weights in W prime, and then we perform fine-tuning to recover the network accuracy from the pruned network W prime. And then we return the pruned network. As we've discussed in the previous slide, pruning comes with tons of design choices. The first design choice is the saliency or the scoring method. Earliest way of scoring parameters to be pruned is by second-order derivatives. Then, we simply move on with a simple magnitude-based pruning, where we select the weights within a network to be pruned by their magnitude. Other types of scoring criterion is also established, with momentum-based pruning as one of the examples. If you are interested, you can check the list of papers in the reference sections at the end of these presentation files. The second design choice for pruning our neural networks is concerns with how we structure our pruning. The most common methodology is the unstructured pruning, where we treat all the parameters equally. There is also another method called structured pruning, which is when we prune network in blocks, either column-wise or depth-wise. This is commonly used to leverage inference time gains, or in other words, it is used to minimize inference time. The third design choice is regarding the distribution or sparsity budget of our pruning methods. We can do either global pruning, by considering all parameters within the whole network to be equal, or we do it layer-wise, meaning we smartly select how much to prune in each layer individually. This might be useful in some cases, such as mobile net or efficient net, where pruning the first convolution layer in these nets does not provide substantial improvement in performance. The Fourth design choice is scheduling, where we emphasize when and how much to prune. Some techniques consider pruning equal number of parameters every round, while others try to prune at a higher number of parameters in the beginning and gradually decrease the number of parameters to be pruned as the network becomes more sparse. The fifth choice is regarding the fine-tuning method. The most common way to handle this is by continue training the network using the previously trained weights within the network before pruning. Some others try to rewind to the earlier state of the network, which will be explained later, and some others try to reinitialize the network entirely. The last design choice is true dynamic pruning, where it is possible to regrow weights within prune model in an attempt to maintain some level of sparsity through constant prune, redistribute, and grow cycle. There are three common choices for regrowing weights. The first one tries to do random or uniform regrowth. Some others try to regrow based on gradient information, and others also come up with locality-based and greedy regrowth scheme. For introducing the big picture and different design choices regarding neural network pruning, I'll introduce recent advances in neural network pruning, where some of the methods try to explain neural network pruning from different perspectives. To examine why neural network pruning is effective in compressing huge neural network, I'll try to explain about the lottery ticket hypothesis, which supports this claim. Lottery ticket hypothesis states that a randomly initialized dense neural network contains a subnetwork that is initialized in a way such that when we train it in isolation, it matches the test accuracy of the whole neural network. To find such subnetwork, which we often refer to as the winning ticket, we employ iterative magnitude pruning, or we call it IMP. In this method, we first try to initialize the network randomly, and then we train the network on some iteration t star, and then we prune portion of the parameters inside the network, and then we reset the remaining parameters to the original state. And we perform this process iteratively until we reach a desired sparsity within the network, and we call it as the winning ticket. So here are some of the experiment results regarding the iterative magnitude pruning in different settings. First, we observe how random reinitialization and retraining pruned networks lead to deteriorated performance as we gradually come into smaller subnetwork. The second figure shows that in experiments using LeNet on MNIST, by not employing hyperparameter adjustments, iterative magnitude pruning is able to achieve sparse subnetworks that are able to outperform unpruned dense subnetworks in fewer training. Also, the last two figures below shows that iterative magnitude pruning can also find subnetworks that's favorable for tasks at hand. It also shows how weight initialization of subnetwork is special in terms of learning dynamics. So what's next after lottery ticket hypothesis? Some of these works try to come up with different approaches for the iterative magnitude pruning after we are done with the pruning procedure. The first method is to employ generic fine-tuning, where remaining weights are trained from their final trained values using the final learning rate of the original training procedure. The second method tried another technique called weight rewinding. In this scheme, remaining weights are reset to the value of a previous SGD iteration k, with these weights retrained using learning rate schedule from iteration k onwards. The last method is called learning rate rewinding. In this method, instead of rewinding weights and setting back the learning rate schedule, we simply use final unpruned weight and only reset the learning schedule up to some iteration k. Now, one might wonder how each of these methods fare against each other. So the first important part is that weight rewinding and retraining procedure outperforms simple fine-tuning and retraining in both unlimited and fixed budget experiments. The second important claim is that learning rate rewinding is outperforming the weight rewinding technique. So it is the most optimal way to find the optimal sparse subnetwork within the lottery ticket hypothesis. And lastly, network that is trained via lottery ticket hypothesis using weight rewinding scheme is the state-of-the-art method for pruning at initialization in terms of accuracy, compression, and search cost efficiency. If you are wondering what pruning at initialization is, I'll explain it later in the next slide. So what is pruning at initialization? Pruning at initialization is a pruning technique that is utilized to detect winning tickets with little to no training. The main motivation of this technique is to save the model overall training cost, and we can see it as an approach in observing the effect of pruning while pre-trained model is absent. There are 4 methods that I'll explain in here which employs pruning at initialization. The first method that starts this trend is called SNP, also known as single-shot neural network pruning. This method tries to preserve weights with highest effect on the loss. And then the second method is called GRASP, which is called gradient signal preservation. Instead of preserving weights with highest effect on loss, GRASP tries to remove weights that reduce gradient flow and preserve ones that increase gradient flow. The third technique is called SynFlow, which stands for synaptic flow. This method tries to reach maximum sparsity before layer collapse. For those of you who wonder what layer collapse is, it is a phenomenon that occurs when an algorithm prunes all parameters in a single weight layer, even when prunable parameters remain elsewhere in the network. The most recent method that applies this paradigm is PEW, also known as paths with higher edge weights. In this method is the method where large number of paths and higher edge weight magnitudes leads to faster convergence and better performance within the network. These are the detailed procedures of pruning at initialization methods that we've discussed in the previous slide. For SNP and GRASP, it can be noticed how training data is still being utilized, and the pruning procedure takes only 1 iteration in the beginning. For SynFlow and PEW, we observe how both methods uses no training data at all, and both methods are done iteratively. All of these methods are basically very similar in terms of the way they are conducted to one another, with different scoring rules in what to prune inside a dense network. You might be interested in acknowledging ways of pruning neural networks against one another. However, most of existing pruning literatures tends to not reveal full experiment setups, use too few and incompatible combinations, omit comparisons with each other, and fail to control for confounding variables. As a result, one paper proposes ScreenBench, a benchmark to evaluate pruning methods in 5 different categories listed below. For methods with magnitude, we consider weight magnitudes as scoring criteria, whilst gradient magnitude considers both factors as a scoring criteria. Here are the results of comparison between different classes of pruning techniques on different pairs of architectures and dataset with accuracy as the metric of interest. It can be notably seen that global gradient performs better than global magnitude in CypherVGG on low compression ratios, but worse in higher compression ratios. And in general, global weight pruning is considered as the best for most of the cases in the figures attached here. So how about the early pruning methods? There is another study conducted to compare pruning at initialization methods against pruning after training methods. As you can see in the figure here, experiments on FIVGG16 and 3 ResNets suggest that most of early pruning techniques outperforms random early pruning methods, but sometimes being outperformed by magnitude-based pruning at initialization. And most importantly, none of these early pruning methods outperform the magnitude pruning after training method, which is considered the best pruning method. To conclude, current early pruning methods still fail to detect specific connections that define the optimal subnetworks in deep neural networks. As a future research direction of pruning, one possible direction that we can take is to improve current methods or research new methods that find specific ways to prune instead of proportions in neural network layers. Also, we need to come up with better scheme in early training pruning or pruning and initialization to compete with the pruning after training methods. Lastly, another possible research direction to be taken with regards to this scheme is by considering scoring techniques other than magnitude and gradients for early pruning. This is the end of my topic review. Thank you for listening.